Today we're taking you inside one of Europe's most advanced steel facilities, Sarstal-Ascoval, located in Saint-Saulve in northern France. This place isn't just a factory. It's a monument to what happens when old-world craftsmanship meets 21st century engineering. Now, Sarstal-Ascoval is a 100% electric steelworks, meaning they don't use a single drop of fossil fuel in their smelting process. Instead, everything runs on an electric arc furnace, or EAF for short. And let me tell you, this machine is something else entirely. We're talking about a furnace that can hold up to 100 metric tons of scrap steel at a time. 3 massive graphite electrodes, each one taller than a grown man, lower down into the vessel and strike an arc so powerful, so searingly hot, that it reaches temperatures above 3,000 degrees Fahrenheit. That's hotter than the surface of the sun as seen from Earth's orbit. The scrap metal doesn't just melt, it surrenders. The EAF at Ascoval is equipped with oxygen lances and carbon injection systems that help control the chemistry of the molten bath in real time. Operators monitor phosphorus, sulfur, carbon, and manganese content with laser precision sampling. Once the steel reaches the exact chemical specification, and we're talking tolerances measured in hundredths of a percent, the furnace tilts, and thousands of gallons of liquid steel pour into a ladle like something out of a mythological forge. From the ladle, the steel moves to the continuous casting machine. This is where liquid metal becomes solid bar stock. The molten steel is poured into a water-cooled copper mold that shapes it into a round billet. As it moves through the machine, a series of water sprays cool the outer shell while the core remains liquid, a delicate dance of heat and physics. By the time the strand exits the caster, it's a solid round bar, glowing amber, ready to be cut to length by a flying shear. What you end up with are precision round steel bars, the raw material for bearings, axles, gears, and tools that keep the modern world turning. At Sarstal-Ascoval, every single bar is traceable from scrap to shipment. That's not just good manufacturing. That's a standard of excellence that would make any old-school craftsman proud. If you've ever looked at a propane tank, a pressure vessel, or the end cap of a large industrial boiler, you've seen the result of a process called dished end forming, even if you didn't know it at the time. And nobody in the world does it quite like Flanges PA, an Italian company with over 50 years of engineering excellence tucked under its belt. Flanges dishing press, sometimes called a flanging and dishing machine, is an absolute beast of precision engineering. We're talking about hydraulic presses capable of exerting forces between 200 and 4,000 metric tons. The machine consists of a heavy steel frame, a central punch die, and a ring die at the periphery. Together, they press a flat metal blank, which could be anywhere from a quarter inch to several inches thick, into a perfectly curved hemispherical or elliptical dome shape. Here's how it works. A flat, circular plate, often cut from high-strength carbon steel, stainless steel, or even titanium, is placed over the ring die. The press slowly descends. As the central punch makes contact and drives the metal downward, the material flows outward and inward simultaneously, taking on a concave dome shape. The flanging process then bends the outer edge of the plate upward, creating the mounting lip you see on real-world pressure vessels. What makes Flanges machines special is their integrated CNC control system. Operators can program the exact stroke depth, forming speed, and pressure profile for any given material thickness and alloy. Sensors monitor springback in real time and automatically compensate, ensuring every dome comes out within tight dimensional tolerances. No guesswork, no rework. There's a quiet kind of power in watching a ring, a simple circle of metal, being shaped into something that will eventually hold a jet engine together or keep a massive wind turbine spinning through a storm. That's the world of forged ring manufacturing. And at Yubin Factory, they do it at a level of precision and scale that genuinely takes your breath away. The process starts long before any machining happens. Large billets of steel, or sometimes aluminum, titanium, or specialty alloys, are first heated in a gas-fired furnace to their forging temperature, which can range from 1,800 degrees Fahrenheit for aluminum alloys all the way to 2,300 degrees Fahrenheit for steel. Once the metal is at temperature, a hydraulic press punches a hole through the center of the billet, creating what's called a preform, basically a thick metal donut. This preform is then placed onto a ring rolling mill, one of the most fascinating machines in all of metalworking. The ring rolling mill uses two main rolls, a drive roll and an idle roll, plus a pair of axial rolls to control the height of the ring. As the driven roll rotates, it squeezes the preform against the idle roll. This compression forces the metal to flow outward, growing the ring's diameter while reducing its wall thickness. The ring literally grows before your eyes like a slow-motion explosion of geometry. At Yubin, the ring rolling process is guided by CNC controls that continuously adjust roll pressure and feed rate based on real-time diameter measurements. This is critical. Overshoot the diameter by even a few millimeters, and the ring is scrap. The tolerance windows are unforgiving. Once the ring reaches its near-net shape, it moves to the machining floor. This is where vertical and horizontal CNC lathes and milling machines go to work. Boring operations hollow out the inner diameter to exact specifications. Facing cuts level the top and bottom surfaces. Profile turning creates grooves, flanges, or tapered features depending on the application. Every step is measured with coordinate measuring machines, CMMs, that scan thousands of data points across the ring's surface and compare them to the original CAD model. If something is even slightly out of tolerance, the system flags it immediately. Nothing ships unless it's right. When a part is too big to spin horizontally, you flip the whole concept on its head. Literally. That's the engineering logic behind the dual-column CNC vertical lathe, one of the most impressive machine tools in heavy industry. Unlike a conventional lathe, where the workpiece rotates on a horizontal axis, a vertical lathe mounts the part on a large rotating table, called a work table, that spins on a vertical axis. The cutting tool travels downward from one of two overhead tool heads, each mounted on a bridge, spanning the two massive columns that give this machine its name. These work tables can range from 3 feet to over 30 feet in diameter, capable of holding workpieces weighing hundreds of tons. The CNC control system manages everything: spindle speed, tool feed rate, depth of cut, and multi-axis tool positioning. Operators program complex turning profiles, internal bores, external tapers, face grooves, and thread forms, with tolerances often held to within 0.005 of an inch. This machine is the go-to for large flanges, turbine housings, gear blanks, and massive rings. It's brute strength and precision engineering working in perfect harmony. There's an art to peeling wood, and when you add CNC precision to that ancient craft, the results are something worth watching. The 4-foot custom-speed CNC rotary spindle peeling machine is the workhorse of modern plywood manufacturing, and once you understand how it works, you'll never look at a sheet of plywood the same way again. Here's the basic concept. A raw log, typically poplar, birch, pine, or eucalyptus, is loaded between two powered spindles that grip each end. The log is then set spinning at high speed, while a long, razor-sharp knife blade is slowly fed inward toward the log's center. As the log rotates, the knife peels off a continuous, paper-thin ribbon of wood veneer, like unrolling a carpet from a cardboard tube. What makes the CNC version of this machine so remarkable is the variable speed control. As the log's diameter gets smaller during peeling, the machine automatically increases the rotation speed to maintain a constant surface speed at the cutting edge. This keeps the veneer thickness perfectly uniform, usually between 0.5 mm and 3.2 mm, from the first peel to the last. Without this compensation, the veneer would taper unevenly, creating waste and weak spots in the finished plywood. The machine also features a pressure bar positioned just ahead of the knife. This bar compresses the wood fibers immediately before cutting, preventing the veneer from splitting or checking as it's peeled. The result is a long, smooth, unbroken sheet of veneer that rolls out onto a conveyor for drying and layering. Modern CNC peeling machines can process a log in minutes and achieve material recovery rates above 70%, turning what used to be wasted wood into valuable, usable product. From forest to factory to your furniture, efficiency has never looked this good.